So, in the last lecture I had told you that if the number of states are finite of a Markov process, then all states cannot be transient, right. We had argued it out that if the system has to go on, then because transient states will be visited only a finite number of times. So, if there are finite number of states, then the process must come to an end in a finite number of time. But since the process has to go on, therefore, if the number of states is finite, then all states cannot be transient. But the argument does not hold when the number of states is infinite, and so I said I will give you an example that when the number of states are infinite, it is possible that all states of this process may be transient, right. And this is what we want to talk about today, and this is so giving you an example when all the states are transient. Okay. Now, random walk is a very interesting and important process, and I hope that after having read about it, now you will be able to recognize situations or processes, stochastic processes which follow which follow the behavior of a random walk. Okay. So, this is now a Markov chain when the state space consists of the integers I varying from can take the value 0 plus minus 1 plus minus 2 and so on. So, that means I am numbering the states by minus 1 plus 1 plus 2 minus 2 0 and so on, and so this can go on for infinite number. The number of states is not finite, this is a infinite state situation. Okay. And then the transition probabilities. So, if you go forward, that means if you transition from state I to I plus 1, the probability is p, and if you transition from I to I minus 1, that means if you go backwards, the probability is 1 minus p. Okay. And this is for I varying from 0 to plus minus 1 plus. So, therefore, the probability remains the same. Essentially, it is going forward, the probability is p, and if you are going backwards, then the probability is 1 minus p, okay, for some any p varying between 0 and 1. So, therefore, for different values of p, you will get different random walks. This is the idea. And diagrammatically, if you look at the transition diagram, the transition diagram simply says that. So, these forward probabilities are p and the backward probabilities are 1 minus p. Okay. So, from minus 1 you can go forward, then you will go to state 0, and from 0 if you go backwards, you will go transition to the state minus 1, and the corresponding probability is 1 minus p, and therefore, this process can go on either side. So, this is your transition diagram. Okay. And so, you see that from here that all states communicate, right, because from anywhere to you can go anywhere. By forward movements, if you want to go from minus 1 to 2, you can go here, then you can again come here and so any possible path is there, but you can transition from any state to any state. So, all states communicate. Okay. And so, therefore, either all states will be recurrent or all states will be transient, because remember the recurrent states will form a class. So, if they form a class, then within a class all states must communicate with each other, since it is already true that all the states communicate. Therefore, all the states will either be, so they are all in one class. So, they will either be recurrent or transient. Okay. And so, here again remember I had defined for you a recurrent state via the probabilities of first passage probabilities. And remember, we had said that if f I is equal to 1, then the state is a recurrent state, because then there is a positive, there is the event that it will recur back to itself is a certain event, right. And if f I is less than 1, then we had said that the state is a transient state. And then using an alternate characterization of a recurrent and a transient state, we had also said that if from here we had said that if p I I summation, this will be summation p I I n varying from 1 to infinity. If this goes to infinity, then the state I is recurrent, and if this is less than infinity, then the state I is transient. So, this was another characterization. So, that is what we will use here. And since all states are behaving in exactly the same way, because the probability is the same of going forward or backward. So, it is enough if we consider sigma n varying from 1 to infinity p 0 0 n. So, let me just look at the behavior of this expression, and if this is I can show that this will be a divergent series, that means it will go to infinity, then I can conclude that state 0 is recurrent, and since they all the states form one single class, therefore, every state is recurrent, and if sigma n varying from 1 to infinity p 0 0 n is less than infinity, then 0 is a transient state, which implies that all states are transient. Okay. So, let us now start looking at this expression. Now, for example, if you look at p 0 0 n, that means this is wanting to know that 0, you starting from 0, you will be back in 0 in n steps. So, since you can see from here from the red diagram that you can return back to 0 only in even number of steps, in even number of transitions, right. If I go here, then I can come back here. So, 2. If I go from here, and then I need another 2 steps backwards, right. Or if I go from here, and then I go here, back here, and then yeah, okay. Or in fact, you can have any possible numbers of forwards and backwards, but they should be. So, in fact, if the number of transitions, if my n is odd, then I cannot come back from 0 if I start from 0, right. So, coming back to itself requires even number of steps, and you can just try to draw number of paths, and you can see that you can go from here, then you can come back here, and again here, and then here. So, all possible ways are there of, but then you will require every time even number of steps. So, therefore, if you look at p 0 0 2 n minus 1, then this will always be 0, right. You cannot transition back to the state starting from 0, you cannot come back to 0 in odd number of steps. So, those probabilities are 0, and for coming back even number of steps, then you require exactly n forward transitions and n backward transitions in any order, right, as I tried to explain from the diagram. So, this will be equal to, therefore, from 2 n you choose n forward steps, forward transitions, and n backward transitions. So, therefore, the probability p 0 0 2 n will be like this, right. Choose n from 2 n transitions, and then p transitions forward, and n transitions forward and n transitions backward. So, probability of backward transition is 1 minus p, probability of a forward transition is p, okay, and this is 1 minus p. Now, just open up the expression here. So, this is 2 n factorial, n factorial, n factorial, p raised to n, 1 minus p raised to n. I will now use Stirling's approximation, which I have already talked about in my earlier lectures. So, factorial can be approximated by the Stirling's formula, and so this will be 2 n raised to 2 n plus half e raised to minus 2 n, and then under root, we left out the part p raised to n and 1 minus p raised to n. So, this is, and therefore, similarly n factorial can also be written by Stirling's approximation formula. So, n raised to n plus half e raised to minus n, and then there will be a root 2 pi. So, root 2 pi for both of them. So, therefore, it will be 2 pi n raised to plus half e raised to minus n. Okay. Now, we can cross out a few things. This and this gets cancelled out, right, and then you can 2 raised to half we can cancel out from here. So, then I will be left with the root 2 pi, yeah, and okay, this is root, so the root 2 pi was there, because this is root 2 pi and this is 2 pi. So, root 2 pi was left, and then that root 2 gets cancelled by this root 2 here, okay. And then you can just see the simplification here, and this is n raised to half, and so here this is n raised to 2 n, that cancels out with this, right, and then there is a n here, and this is n half. So, you will be left with root n. So, this is root n root pi, and then you have 2 raised to 2 n, which I bring inside here. So, this will be 4 into p 1 minus p raised to n. So, this is the simplification, right. after using Stirling's approximation formula for the factorials, I get back. So, we saw that this series can be approximated by the series n varying from 1 to infinity 4 p 1 minus p raised to n upon root pi n. Now, this I can, the terms I can break up as sum of even terms and odd terms, and here even though I have written the index as n, does not matter, it is a dummy index. So, here it could have been m also, but the idea is that I am breaking up, I am writing p 0 0 n, instead of this I am writing the odd, I am adding up the odd terms and the even terms. Now, the odd terms do not contribute anything to this sum. So, it is only the even part, and so now let us consider the case when p is equal to 1 by 2. So, in that case this will become equal to 1, right, and so the series will reduce to summation n varying from 1 to infinity 1 upon root pi n, which we know is a divergent series, because the power root pi of course is a constant. So, this will be n raised to half 1 upon n raised to half, and we know that this series 1 upon n raised to p n varying from 1 to infinity is divergent for all the values of p less than or equal to 1. This we already know. So, therefore, this is the divergent series, and therefore, since so the state, all the states we will immediately conclude that all the states are recurrent, because the time to return to this is infinity. So, all states are that means sigma n varying from 1 to infinity p 0 0 n. So, this is recurrent, and therefore, all other states are also recurrent. Okay. Now, we have to consider the case when p is not equal to half. So, for p not equal to half, your 4 p into 1 minus p will be less than 1. Remember, because for p equal to half, this is the maximum, this has the maximum value for this term 4 p into 1 minus p is for p equal to half. So, for p less than half, it will be less than 1, right. And so, let me call this term as alpha, let me denote it by alpha. Then we will show that this series converges, and it is simple, you just apply the ratio test. So, take the n plus 1th term divided by the nth term. So, which will be now the n plus 1th term will be 4 p into 1 minus p raised to n plus 1 under root pi into n plus 1, and here you are dividing by the nth term, which is this. So, you have this, and so here you see you are left with 4 p into 1 minus p, and then this root n I bring in the denominator. So, this will be 1 plus 1 by n raised to half, and therefore, the limit of this ratio of the n plus 1th term and the nth term as n goes to infinity will be, you see this will go to 1, and therefore, it will just converge to 4 p into 1 minus p, which is a number equal to alpha less than 1. Whatever the value of p, since p is not equal to half, this number will be equal to something less than 1, right. And so, yeah, so in that case we will conclude that all states are transient states. Now, of course, I had told you that you can look up for whenever, now that you know this random process where it is going backward, forward, and of course, for the transient case, the probability of going forward is different from going backwards, and for recurrent states it was both the probabilities are the same. So, now just on the lighter side, you know, you can say that if there is a drunken man and he is trying to walk on along a straight line, then he will take a step forward, then he may take 2 steps backwards, or he may take 2 steps forward and 1 step backward, or something like this. And so, you know, the wanderings of a drunken man, you can sort of say that the process, the walkings of a drunken man can be modeled as a random walk. Okay. And of course, it will depend on the p, the value of p will depend on how drunk he is, or something like that. Okay. So, that is the that is one of the examples, and then we maybe we will come across some more in the process of this course, or otherwise you can you know, you can now be aware of such a process. Okay. Then we will continue with the classification of the states, and after the transient states, there are also states which are periodic and null states, which are both of which are not of much practical use, and of course, the occurrence is also not that often. So, now you see we have talked of, we said that a recurrent state, it is possible that a recurrent state may have infinite mean recurrence time. that is mathematically this sum may not converge. And remember, for recurrent states, if when we wanted to find out the first passage time and so on, then we did it by finding the mean recurrence time, the MIJs and MII. When we did this, then we assume that this is a finite, that this series will converge. Okay. But but it is possible mathematically that this series may not converge, even though the series, this of course, this is your condition for a state to be recurrent, that is sigma f I n varying from 1 to infinity, which is equal to sigma which is equal to f I, that is the recurrence time, probability of the state coming back to itself, then this is equal to 1. So, for recurrent state this probability has to be 1, because coming back to a recurrent state is a certain event. Okay. So, this series converges, but this series may not converge, which is your mean recurrence time. Okay. And this is such a state we will define as a null state. Okay. So, not much is talked about it, and so we will also not spend much time, but we must complete the presentation of the states of the classification of the various states. And so, for the recurrent states where we assume that this is finite, because then we were solving for MIJs or MIIs, and but there is possibility that this series may not converge. Okay. And this, as I have already said, these are of real practical use, and the probability of being in null state will also go to 0. So, therefore, we will not talk about such states, we will not spend much time on it. But just to complete the discussion, we have also considered the case when this may not converge. Okay. So, this may not be finite. Okay. Now, let us talk about periodic states. So, consider the following transition matrix, and this is the corresponding transition diagram, and you can see immediately from here that from 1 you will either go to 3 or to 4, right, and also from 2 you will go to 3 and to 4, and then again from 3 you may go to 1 or you may go to 2, and from 4 you may go to 1, and from 4 you may go to 2. So, that means there are 2 classes, you can immediately see, because there is no communication between the states here, among the states here and the states here, right. So, it is, you can just, I should not say classes exactly, because these 2 are not communicating and these 2 are not communicating, but they are communicating to the. So, you have communication between the states of this set and this set, and vice versa, right. So, your system will alternate, that means at any time either the system will be occupying states 1 and 2, or it will be occupying 3 or 4, right, because once if you start in 1, then you will either be in 3 or 4, and then if you are in 3, then you will either be in 2 or back to 1, right. So, you either communicate this way or you communicate this way. So, your system alternates between these 2 classes, is that okay? And that you can see by these probabilities also. Okay. Now, so let us, in fact, you can see from here that suppose I go to from 1 I go to 3, then I can come back to this. So, that will be in 2 transitions I can come back from 1 to itself, right, or I can go from 1 to 3, then I can go from 3 to 2, and then 2 to 4, and then 4 to 1. So, that means it will be then in that case it will be 4 transitions that will be required to go from to start from 1 and come back to 1, right. Or and look at the other thing, if you may go to from 1 you may go to 4, then again you can come back. So, again it will be 2 transitions, but if from 1 you go to 4 and then you go to 2, then you will go to 2 to 3 and then 3 to 1. So, it will be, that means you can recur back to state 1 either in 2 transitions or in 4 transitions, and the same story is true for state 2. That means, from 2 you can come back to itself either in 2 transitions or in 4, and the same again for 3 and 4, right. From 3 you may go to 2 and then come back, right, or you may go to 2 and then you may go to 4, then 4 to 1 and 1 to 3. So, all the states can be revisited either in 2 transitions or 4 transitions. Revisited, I mean starting from that state, you will revisit it either in 2 transitions or in 4 transitions, right. So, you can see that there is a periodicity, and so let us now make a definition. So, we will say that a state which can occur at time periods m, 2m, 3m and so on, where m is some integer greater than 1, is called a periodic state of period m, right. So, therefore, using this definition, you can say that all the states of this particular chain are periodic of period 2, right. A state for which no such m greater than 1 exists is called aperiodic. So, if I cannot find, so here of course, the understanding is that it actually the word should have been a state which can occur at times period m, 2m. So, that means, if you are starting from that particular state and then it occurs again at period m, 2m, 3m, then the period is m. So, that part is understood here, right. That means, you are starting from a particular state and then if you can visit it at regular intervals of periods m is some integer which is greater than 1, then that state will be periodic. So, in this case of course, what is happening is that your all the states are periodic. So, this is one particular example, but of course, you can have a situation where you may have some recurrent states, and so these are also recurrent, but not in that sense. In this see here, yeah. So, we will just see that there will be no this thing, there will be yeah, you can say that this series, in fact, the periodic state, you already know that the you are going to visit it at a particular time. The probability of visiting it at regular intervals is there, it is a positive probability. So, for periodic states, we said that the coming back number of transitions has to be a factor of some integer greater than 1, that means m, 2m, 3m and so on, then we will say that it is a periodic state of period m. Now, of course, on the transition diagram, if you can see that all walks starting from I, walks or paths, whatever we have been saying, starting from I and returning to I are of length m, 2m and so on, where m is greater than 1, then I is a periodic state and the period is m, right. And so, for the example that we just considered, I showed you that any state you start from either 1 or 2 or 3 or 4, you can come back to them in either 2 transitions, 4 transitions, 6 transitions, and so we concluded that the period for each of the states was m, right. Now, if you can find a walk of length 1, that means, if there is a loop for a state, that means, you can come back to it in one step, or if you can find 2 walks which have relatively prime lengths. Okay. That means, one walk may be of length m 1 and the other may be of m 2 and they are relatively prime, they have nothing in common, then again you can conclude immediately that the state is not periodic. That means, it is aperiodic, right, because if there can be 2 paths of length that starting from that state and coming back to it either in m 1 transitions or m 2 transitions, and these are relative, then certainly there cannot be anything common, and so there cannot be a period to that state, right. Or if there is a loop, then certainly it is not a periodic state, right. That is another way. So, we are just trying to look at various ways in which you can characterize a periodic state, and then again if it turns out that your mth power, that means the PM transition matrix raised to power m, if this is greater than 0, that means all components are, all entries of this matrix are positive for some m, then no. So, actually it is not difficult to show that if you are given that PM is all components of the matrix PM are positive for some m, then it can be easily shown that your matrix PM plus 1 will also be positive. That means, all entries of the matrix PM plus 1 will be positive, and this you can see immediately from here. See, PM plus 1 can be written as P into PM. Now, let alpha denote the okay, let alpha denote the minimum of Pij m greater than 0, and then we are saying yeah. So, because every element of P m is positive, so take the smallest one, and that smallest one I am denoting by alpha, and that will be positive, right. Now, consider the ijth element of P m plus 1. Okay. So, that will be ith row of P multiplied by the jth column of P m, right. And so, this is P I into P j m, right. Now, you see that when you multiply the ith row with the jth column and replace each entry of the jth column by alpha, because all other elements are bigger, right. So, I am writing the smallest possible number for each of the entries of the jth column, and then so it will be P I 1 plus P I 2 plus P I n times alpha, because and since the rows add up to 1. So, this will be equal to alpha. So, therefore, the ijth entry of P I j of the matrix P m plus 1 is greater than or equal to alpha, which is also positive, and this holds for any elements I j of P m plus 1. So, therefore, matrix P m plus 1 is also positive. Now, since all the entries of P m are positive, so it seems that pick up any I, then P I I m is positive. That means, there is a path of length m from state I to I, and since P m plus 1 is also a positive matrix, P I I m plus 1 is also positive, which implies that there is a path of length m plus 1 from I to I. And now, by our definition, you see m and m plus 1 for any m integer, positive integer, there are co-prime numbers. So, we have shown that there are two paths from I to I of co-prime lengths, and hence by our definition the state I cannot be periodic. It will be by our definition it will be aperiodic. So, and since this is true for all I, therefore, no state is periodic. So, the proof was simple. I had asked you to do it on your own, but I realized that we can show it right here and figure it out. Okay. Think about it. Now, of course, periodicity is a class property, as we have shown. That means, you will have just as we defined that all states in that class would be periodic and having the same period, right. So, we can put together all states which are periodic of the same period, right. Now, consider this example that we looked at, the transition diagram for 4 states, and we saw that every this thing, yeah, okay. I did not write down, I think, the probabilities, or okay, let us not forget. So, let us see, given that matrix P, then you have P square. If you now multiply P with itself, then you get this matrix, right. So, your P was if I yeah, we just wrote down in the last time we said that one is going to 3 or 4. So, there were numbers here 1 by 3, 2 by 3 and so on. So, you had positive numbers here and you had positive numbers here, these were zeros, and then so now when you take P square, the numbers, the non-zero numbers shift here and the non-zero numbers from here shift here, right, and each entry becomes half, right. And then P 3, when you now take P 3, that means you multiply P 2 with that transition matrix P, then you will get, so these entries will shift here and these entries will shift here. So, this is how, so I am just wanting to through powers of the transition matrix, I am just trying to show you what is happening. And then finally, when you take P 4, the halves will again shift here, okay, equal to P square, which you would expect, because every state of the system had period 2. So, therefore, after 2 iterations of 2 transitions, this will the transition matrix will be the same. So, P 2 will be P 4 will be equal to P 6 and so on, right. And similarly, P 5 will be equal to P 3 and this is equal to P 3, yeah, this will not be equal to P, that is true, yeah, okay. So, P 5 will be P 3 and then all other powers will continue, all odd powers will continue to be the same, because then you see P 3 tells you a probability of going from 1 to 3 in 3 steps. So, that is what will happen, right. It will come back to itself and then go back, and so from here it can go to 3 and 4 and again in 3 steps. So, either it happens, see, you had 1 here and then you had 3, right, and you had 4. So, this was it, right. Then if you come to 3 in one step, and then if 3 you cannot go back to it cannot come back to from 1 to 3, you want to come back in 3 steps. So, you will either go to here or you will go here, right, to 2, right, and then you may come back to 2, 3. So, it will take 3 steps to come from 1 to 3. So, starting from 1, if you want to come back to 3, then you will have to require 3 steps, because in 2 steps you can either from 1, starting from 1, you can either come back to 1 or to 2. And so, therefore, you will need odd number of steps to go from 1 to 3 or to 4. So, either in 1 step or in 3 steps or 5 steps and so on, because the even transitions are reserved for coming back either to this thing. So, that means within a class, and that is why we said that this is this and this is this. Of course, they all had the same period, but here what we are saying is that you can go from 1 to 3 and then 3 to back, or 1 to 4 and 4 to 1 and so on. Okay. So, this is what is happening, and so you see that your PIIN. So, if you see here in the first matrix, your PII, so P111 was 0. Now, it is half. Then again in P3 this number is 0, and similarly all these numbers are 0, and all these numbers here in P2 are half, right, and then in P4 again they are half, and in P5 when you again look at it, all the numbers, all these PIIs will be 0. So, this limit does not exist, right. So, limit PIIN and going to infinity does not exist, actually it oscillates between 0 and half. So, therefore, and this for the first condition for the, so this series will also not converge, this if you want to take the summation, but anyway these are not the first step transition probabilities. So, all we are saying here is that limit PIIN as n goes to infinity does not exist, this limit, and also so the summation will also not exist. This is not the convergent series PIIN n varying from 1 to infinity, but will not be a convergent, because the necessary condition for this series to converge is that the nth term must go to 0 as n goes to infinity. So, here this limit does not exist. So, therefore, I cannot say anything about this series also. Okay. So, now after having looked at all possible states of a Markov process, the conclusion is that if the process is ergodic, then, and of course, finite number of states, then the steady state probabilities can be found by solving system of linear equations, as we saw, right, by solving this matrix equation pi equal to pi p and sigma pi I varying from 1 to n is 1. So, with this condition, because otherwise the solution here is not unique. So, we saw that when you put this condition, we will get a unique solution if your system is ergodic, that is finite number of states and all states are recurring. Okay. And of course, so therefore, this system does not contain any transient, periodic or null state. So, this was one convenient way, but then we saw that there were other states also. So, for transient and null states, probability of being in that state is 0, and so and of course, periodic state also do not possess steady state probabilities, right. So, when the state possesses a steady state probability, then we saw we can solve it by this linear equations, adding this equation to it, but otherwise periodic states, as we have seen, do not possess steady state probabilities. For transient and null states, the probability of being in that state goes to 0 as the process continues for a long time. And so, we have finally sort of completed this argument and said that if when you know that the system is ergodic and so on, the finite number, then you can solve for steady state probabilities using a system of linear equations. For others, we have seen methods how to classify and how to decide that the state is periodic and it is null or transient. Okay. Now, the thing is that periodic and null states have are not much of practical use, and they don't their occurrence is rare. So, we will not talk about them, but transient states, transient processes are there. That means, there are a lot of practical situations where the process does not continue for a long time. So, it is and therefore, we call them reduced Markov processes, and so they are transient in the sense that after a while the process comes to an end. And so, that we would like to look at in more detail, because there are situations where your processes are not supposed to continue for forever, and so we will define them as reduced Markov processes, and we will talk. So, reducible Markov chains, one or more absorbing state and a number of transient states, right, because we are saying that the process will not go on, it will terminate after a short period of time. So, therefore, there will be either one or more absorbing states, and remaining will be transient states. So, again by our discussion we have seen that once you reach an absorbing state, you will not go out of that state. So, the process will terminate, or if you are in a transient state and the number of states are, then you will the number of states are finite, then again after a finite period of time the process will be over. So, this is what we are talking about. So, an interesting example, and that is the gambler's ruin problem. Now, the idea is that the gambler at each play of the game has probability p of winning 1 rupee and probability q of losing 1 rupee. So, there is a game, and I will tell you why it is called gambler's ruin problem. So, now successive plays of the game, it should be y s plays of the game are independent. So, successive plays are independent, that means it does not, whatever the outcome of one play, the game goes on independent of what has happened, and the gambler will quit playing when he wins rupees n. So, he wants to make a fortune of rupees n, he is hoping for that, and so he will quit the moment he has earned n rupees. So, we want to find out the probability that starting with rupees I, suppose he has this much money with him, the gambler's fortune will reach rupees n before reaching 0, and that is what we mean by the ruin, because if we allow the process to go on, then he will ultimately lose all the money, and that will be the end of his playing the gambling, because then he cannot bet anymore. So, let us look at the transition diagram. So, here what we are saying is that see, with 0 he cannot play, because he has no money to bet. So, he stays here. Otherwise, if he has rupee 1, then he can either lose that rupee and come back to state 0, or he will win and he will go to with probability p, and then he will go to 2. That means, he will have 2 rupees. So, the state is described by the amount of money he has, and that is how we are using these integers to describe the situation, right. And then of course, again if he has 2 rupees, he bets and he loses that rupee, then he will again revert back to having rupee 1, and so that will be the state. So, this the diagram, and finally, at n minus 1, when he has n minus 1 rupees, he will bet again, and if he wins, he will get n rupees, he will make his fortune. So, we want to compute that, and of course, what we are saying is that he will stop playing. So, there is no going back from here, because he will just quit the game, right. So, this is the whole idea, and so this is now, if you look at it, this is a the duration of the process is finite, and you can see that this is an absorbing state, and you may call this also an absorbing state, and all other states are transient, right, because the moment he has some money with him, he will bet, and then he will either convert, he will either go back to 0. For example, here he will either win and he will go to transient to this transition to this state, or he loses and then he transitions here. So, again this is an absorbing state, and he loses the he just loses all the money, and therefore, the game is over. So, this is what we want to talk about, and I will show, and of course, the whole idea is to compute the probability that starting with rupees I, the gambler's fortune will reach rupees n. And you can say that here of course, so the process here you can immediately see that this is a Markov process, because you are transitioning, and it just depends on where you are. So, your transitioning to the next state just depends on where you are, and it does not matter how you reached 1 or how you reached 2. It just so you can immediately conclude that this is a Markov process, and this is a short period duration. That means, it will terminate if the gambler ends up with rupees n. Otherwise, of course, or if he just loses everything and he is back here. So, starting with the rupees I, we want to find out the probability that the gambler will reach the fortune that he wants to make. the gambler's ruin problem, I have put it as an exercise in exercise 10, which I will be discussing after some time. So, I have after explaining the problem, I have now left it to you to work out the details, and let us hope that you enjoy doing it and you are able to compute the probabilities. But while discussing the exercise, I will also give you some hints and try to show you how to go about it. Okay.